Hey, welcome back everyone. It's Kevin Wallace. This is our fourth of four videos focusing on IP addressing. You might remember we started out with a binary numbering review, understanding how to convert between binary and decimal. We followed that up with a basic subnetting video where we learned how to do a bit of design. We learned how to create a subnet mask that would accommodate a certain number of subnets or a certain number of hosts. In the advanced subnetting video, we answer the question, what are those networks? What are the address ranges for the subnets that we just created? And we gave you quite a bit of practice with that. We're going to wrap things up in this video with an introduction to IP version 6, because up till now we've been focusing on the most widely deployed type of IP addressing out there, and that's IP version 4. However, the future is most definitely in IPv6, and the reason is the world is simply running out of IPv4 addressing. In fact, I was reading an article the other day that was describing how all of the classful addresses, classes A, B, and C that were publicly available, they've all been given out. I remember when I used to work at a university back in the early 90s, we wanted to get on the internet with our own block of addresses, so we applied, and we got this nice big Class B network all to ourselves. Those are all gone now. There are no more classful networks to give out. That's not to say that more people cannot come on the internet. Obviously, service providers have big blocks of addresses that they own, and they can give one or two addresses or however many addresses to customers, and the customers could use network address translation to convert between the one or the few publicly routable addresses and private addresses inside of the company. So it's not as if we're not able to add more people on the internet today, but it's certainly not a scalable solution. The future is in IPv6. Let's begin our discussion by looking at the benefits of IPv6. And I would say one of the biggest benefits of IP version 6 is what we've been discussing. We're running out of IPv4 addresses. However, with IPv6, we have a plethora of addresses available. In fact, there is approximately 5 times 10 to the 28th addresses for every person on the planet. 5 times 10 to the 28th. A 5 followed by 28 zeros. I don't even know what that number is. It's a really big number. There's no way in our lifetime that we would ever run out of IP version 6 addresses. I mean, every single thing you own, every article of clothing you own could have its own IPv6 address, and you'd still never run out of IP version 6 addresses. So IP version 6 definitely handles the issue of running out of addresses. Next, it's a bit more simplified when you look at the header, compared to an IPv4 header, that is. An IP version 4 header has 12 fields. An IPv6 header, it only has 5 fields. Also, we get rid of broadcasts with IP version 6. With IP version 4, remember what a broadcast does? A broadcast is sent out to all devices on a subnet in a broadcast domain within a VLAN, and all the devices receive it, and they have to look at that broadcast frame even if it's not destined for them, and if they don't need it, then they discard it, but that takes processing away from all the devices on this subnet. There are no broadcasts with IP version 6. There's something else we'll talk about in a few moments called an anycast. Something else that we get away from in IP version 6 is fragmentation. With IP version 4, an interface on a router can have a maximum transmission unit size set. How big can a packet be and be transmitted out of that interface? And if a packet is bigger than the MTU size, the packet gets fragmented. It gets chopped up into maybe a couple of smaller packets that can be sent out of that router interface. Well, some packets have a do not fragment bit set. They will fail if the router tries to fragment them, and fragmentation can also cause extra headers on the network because we're creating extra packets. Well, here, there is no fragmentation because the MTU is decided upon for every single session. There's an MTU discovery performed for every session, so no session will need to have its packets fragmented. And we've been talking about IP version 4 being the most widely deployed IP addressing scheme out there today. Obviously, this is not going to be a forklift upgrade when you migrate to IP version 6. The great news is IP version 6 addressing can coexist with IP version 4 addressing during a migration. Many operating systems will run what is referred to as a dual stack. They will simultaneously run IP version 6 and IP version 4. As we're going over a network, maybe as we're trying to send traffic between a couple of routers and it's an IP version 4 link between those routers, we could create a tunnel, an IP version 4 tunnel, and what we can do with the tunnel, we can encapsulate some other type of traffic, such as IPX or AppleTalk, or IP version 6. We can encapsulate whatever that other protocol is and encapsulate those packets from that other protocol inside of IP version 4 packets and send them across the tunnel. Well, we can send IPv6 packets encapsulated in IP version 4 over an IP version 4 tunnel. So there is a way to coexist during a migration. Let's check out the address structure of IP version 6. While IP version 4 was a 32-bit address, IP version 6 is a 128-bit address. And the addressing can be written in a dotted decimal notation, as indicated with the X's on screen. The X's in this case, those are hexadecimal numbers. A hexadecimal number is in the range of 0 through F. The way this counts is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. There are 16 possible values for a hexadecimal digit. And 16 values, how many bits would it take to get us 16 values? 4 bits. 2 raised to the 4th power is 16. So if we do the math, we can see that we've got these 32 hexadecimal digits. They're 4 bits each. 32 times 4, 128 bits. We've got a 128-bit IP version 6 address. Here's an example of what that address might look like. Notice that we have groups of 4 hexadecimal digits, and then we have a delimiter of a colon, and another 4 hexadecimal digits, and another delimiter of a colon. There are 8 of these fields separated by colons. And this could be a little bit unwieldy to deal with. There are a lot of hexadecimal digits here. When it comes time to assign addressing, that could be a lot of work. It might be error prone. So you might want to check out something called the EUI64 format, the Extended Unique Identifier. This can cause the router to automatically populate the rightmost, the low order 64 bits in an IP version 6 address based on the router interface's MAC address. So we don't have to make up that address. It can become populated automatically. And getting back to how long this address is, another bit of good news for you, there are rules for abbreviation. We can squeeze this down into another address which is still perfectly valid. Here's the first rule, is we're looking at these 8 fields, the fields that are separated by colons. Any leading zeros in a field, they can be omitted. We don't have to enter those. And if we have a field containing all zeros, and maybe after that there's another field containing all zeros, well, contiguous fields that do contain all zeros, we can represent those contiguous fields with a double colon. Of course, you're only able to do this one time when you're abbreviating an IP version 6 address. Otherwise, if you had, for example, A, B, C, D in the first field, and you had a colon, colon, and then you had 1, 2, 3, 4 in the next field, and then another colon, colon, you wouldn't know the number of contiguous all zero fields represented by those 2 different double colons. You see, if we just do it one time in an IP version 6 address, well, the device knows that there are 128 bits. So if you've specified 64 bits and you've got this double colon, it can deduce that that double colon represents another 64 bits, which are all zeros. Let's go through an example. Here's that address we saw on the previous slide. ABCD colon 0, 1, 2, 3. Remember, we can omit the leading zero, so we're going to get rid of that 0. 40, 40, nothing we can really do to abbreviate that field, but then check out 0, 0, 0, 0, colon 0, 0, 0, 0, colon 0, 0, 0, 0. We've got 3 fields in a row, 3 contiguous fields that contain all zeros. We could represent that with a double colon. And then we've got 0, 0A. We can omit the leading zeros, so that's just going to be an A. Colon 0, 0, 0B. We're going to omit those leading zeros to give us just a B. Here's what that abbreviated address looks like. We've got ABCD colon 1, 2, 3, we omitted the leading 0 in front of 1, 2, 3, colon 40, 40. There's nothing we could do to abbreviate that field. But then we had our 3 fields of contiguous zeros. We represented those fields with colon, colon. Then we did an A because we omitted the 3 leading zeros in front of the A, colon B because we omitted the 3 leading zeros in front of the B. So this is a much more manageable address, a much more easily typed in and a less error-prone to type in address by using these abbreviation rules. And since IPv6 is on its way to taking over as our routed protocol in our networks, we need routing protocols to advertise IPv6 networks. Let's think about how we can educate a router about IPv6 addresses. One way is to simply do static routes. Nothing wrong with that. We can type into the router to get to this IP version 6 address, go to this next hop IP version 6 address, or go out of this interface. RIP, the Routing Information Protocol, it's been around for a long time. It's not considered very scalable. It's got some other issues. And RIP version 1 and RIP version 2, they will not support IPv6. However, RIP-NG, RIP Next Generation, will support IPv6. OSPF version 3 will support IPv6. However, OSPF version 2 does not support IPv6. If you're using ISIS, there is ISIS for IPv6. It's very similar to the version 4 ISIS routing protocol. There are a few IP version 6 extensions added. For example, there are new TLV, type length value attributes, and there's a new protocol ID, but it's pretty similar. If you're using BGP to advertise maybe out to a service provider, there is multi-protocol BGP, which will allow you to advertise protocols in addition to IPv4, such as IPv6. And the Cisco proprietary EIGRP protocol, that will work with IP version 6. And do you remember we were mentioning earlier that IP version 6 does not do broadcasts? Let's see what it does do. There are 3 types of data flows for IP version 6. Unicast is where we're sending from one IP version 6 address directly to another IP version 6 address. Multicast is when we're sending from an IP version 6 address to a multicast group. With IP version 4, we can have multicast, and in IP version 4, you might remember from one of our previous discussions that a Class D IP version 4 network, where the first octet is in the range of 224 through 239, that's the range of multicast addresses for IPv4 addresses. For IPv6 addresses, the reserved range is in that first field, FF00 through FF0F. And that's just in the first field, so there are tons of multicast addresses available for IP version 6. Here's the new one. Here's what we did not have in IP version 4. Instead of broadcast, we have Anycast. With Anycast, we can take a single IP version 6 address and assign it to more than one device. And then, when we're sending to that IP address, the router can decide which of those devices appears to be closest, and traffic can be routed to what is determined to be the nearest device that has that IP address. Let me show you an example of each of these. Here's a topology for Unicast. We're sending from a multicast address of AAAA:1. Notice how I used the abbreviation rules there. We're saying that the first field is AAAA, the last field is 0001, everything in between, all zeros. I'm sending to a destination address of AAAA:2. That's Unicast, from one IP address to another IP address. This is called one-to-one communication. Multicast would be called one-to-many communication, because here I'm sending from one IP version 6 address, AAAA:1, and I'm sending to a destination address that's a multicast group number. Remember that range of addresses that I showed you earlier that I said was reserved for multicast? One of those addresses is FF00:A. And notice we have a couple of hosts that have joined that multicast group, specifically the PC with an IP version 6 address of AAAA:2 and the PC that has an address of AAAA:3. Both of those PCs have joined the multicast group of FF00:A. So when we're sending to that group address, that traffic is received by both of these PCs, but it's not received by the PC with the address of AAAA:4 that did not join that group. And the third data flow, instead of being one-to-one or one-to-many, it's one-to-nearest. Here, AAAA:1 is sending to an address of AAAA:2, just like we had in the Unicast example. Here's what's different. We've got 2 different servers, Server A and Server B, that have the same IP version 6 address. They both have the address of AAAA:2. However, from the perspective of router R1's routing table, in this example, it considers the path via R2 to be a better path, a nearer path. So that's what Anycast does. It's a one-to-nearest flow. So the packet's going to be routed to Server A in this example. Well, that's going to wrap up our 4-part series on IP addressing. Hope you enjoyed it.